All right, we are recording, we are live, audio and video's up. Welcome back to Structures. We have 1 week, and for us, only 2 days left until break because we're going to lecture today, we're going to lecture on Wednesday, and we're not going to meet on Friday. I'm going to give you all the day off. I say here homework 8.1 is graded. I'm actually not sure if that's the case. I'm not sure if the TA got around to that, but that should be graded sometime today. And then your homework 8.2, I extended that deadline to Wednesday because we didn't quite finish what we were doing in class on Friday. I think you could probably reason through where everything's going, but I don't want to make you do that because this is the first time that you've seen this approach. So I really want to give it its day in court, if you will. What we did up until last time, I guess you could say, is the end of part 1 of matrix analysis. And today we're going to finish out that example. And I really place a lot of emphasis on this one particular bar analysis example, because if you understand that, you really do have a conceptual understanding of everything that any software program does, because they all operate the same way. There are some additional details that you need to account for, which will become clear after today's lecture. But by and large, I believe you'll get the process. So let's just go back to make sure everybody remembers what we had done, which, by the way, one of the things that we're going to do today is we're going to finish the example by hand, and then I'm going to show you a couple tips and tricks in Excel that you can use for your homework that's due Wednesday. So we'll do the example by hand first, and then we'll go into Excel and show you how it would work. Okay, let's recall our flow chart. So the 2 blue boxes, again, I think are items that everybody's pretty familiar with. You understand how to create the model, to define the geometry, the joints, the members, the boundary conditions, to define the loading, to define the materials, the section sets, all of that. First thing that the program does, well, let me just go back and say, okay, you understand how to create the model, and then you click that little button called Solve, and it does some stuff in the background, and it gives you what's in the top, the support reactions, the internal member forces, the deflected shape. And keep in mind, if you have the internal member forces and you know the section properties, then you could determine stresses, and if you have the displacements, you could determine strains and all that. But really, the forces and displacements are where it's at, because everything else can be back calculated as a result of those. When you click the little Solve button or the little equals button, what it's doing is everything that you see on the lower 2 portions of the flow chart. It's assembling the stiffness matrix, so it computes a little stiffness matrix for each bar, and then it assembles that into a global stiffness matrix for the entire system. It then collects the global load vector, and that's sort of where we stop, because you have the stiffness matrix for the entire system, and you have the force vector for the entire system. What we now need to do is solve for the displacements, and we need to compute the final results. And so that's kind of what I want to focus on today. Remember, oh, my coffee maker's losing his mind here. Recall some basic ground rules. So again, I'm going to use the term joint and the term node interchangeably, as is I'm going to use the term member and element interchangeably. For the units, make sure that you're converting everything to consistent units before beginning a problem. That doesn't really matter for this problem, but I know on our truss analysis problem that we do on Wednesday, I did keep the member lengths and feet, and so you want to automatically convert those to inches before you even start doing any matrix analysis. Typically in US units, we're using kips for forces and inches for length, and so everything else, section properties, deflections, everything, all material properties, all gets referred to in kips and inches. And lastly, our sign convention. We're considering forces to the right positive and forces upward positive. Same thing with displacements. Displacements to the right are positive, upward forces or upward displacements are positive. And so that, keep that in the back of your head, drill that into your head. Okay. Here's the example we were working on. This is the bar system. Now we've got 4 joints, 4 nodes, and 3 elements. So there were 3 element level stiffness matrices and 1 big old stiffness matrix for the entire system. We were given all the properties for the areas, the E values, the lengths of each of the elements. We know the loads. We've got all that figured out. Let me skip ahead to this next slide, because what I've done here is I've said, here's our progress so far. So on the element level, what we've got is the stiffness matrix for each element. So remember, we computed the EA over L for each element. So we got 100 for element 1, 200 for element 2, and then 100 for element 3. And then we assembled those. And so the first thing I want to point, or really I want everybody to make sure they're clear on, is I want everybody to be clear on how we took these three and we got that. Okay, that's really important. So if you don't understand that, please, this is what we're here to do. So is there any questions on this process called assembly? How you take element level stiffness matrices and assign them to a global stiffness matrix, or a system level matrix, I should say. I want to make sure and not use that term global loosely, but a system level matrix for the entire model. And basically what you're doing is you're using these member codes, like, for element number 1, we have 1 and 2, and so we place those terms in the system level matrix at those spots. And anytime you have a term overlap, for instance, this term is going to overlap with that term, because anytime we have those terms overlap, we just add them. Hence, that's why we got the 300 here. So is everybody okay with that? And I want to make sure chat's responding on this. Everybody good on that? Okay, good. The other thing to point out is we also went ahead and wrote our force vector and our displacement vector. And notice the unknowns. And notice there's sort of like a checkerboard pattern of unknowns. Like everywhere that there is an unknown displacement, we have a known force, because that's the load. It could be 0, but we do know what the force is. So there's a 300 and a minus 125, and that came from the loads that were placed to the system. And everywhere that there is a 0 displacement, there is an unknown reaction. I got a typo there, because that should be R4. Sorry, that right there. That should be R4. So I'll fix that and re-upload later on. But yeah, everybody good on this? Same thing there. That should be R4. Okay, let me erase all this. Let me go back to the notes that we did together in class. Okay, so here's the problem that we did in class. So we did the EA over L's, computed the EA over L's for each element, got the stiffness matrix for each element. Now, one of the other things that's worth pointing out is that we took the flow chart and we canceled a lot of stuff that doesn't affect a bar analysis. And so what I mean by that is for bar systems, we're ignoring the local versus global aspect of that. And I want to be clear, you are going to ignore the local versus global aspect on your homework assignment as well. If there's any confusion there, I guess the best way of thinking about it is assume that all of the stiffness matrices and stiffness values that are given to you on the homework are already in global coordinates. That doesn't mean a lot now, but it'll mean a lot more later on in the lecture. So we've ignored everything with local and global, and again, that goes to a terminology perspective. Anytime I have a lowercase letter that refers to local, and global, it's an uppercase letter, but that doesn't matter for bar elements. And we don't have any member loads, so there's only loads applied to the joints. That's how we formed our joint load vector. So we have our system, and we wrote a stiffness matrix for each one, and then we assembled it into the big old system that you see here. We wrote our force vector and our displacement vector, and so here's where we left off. This is the star of the show. Now, what we need to do is we ultimately want to solve this system, okay? Now, remember, this is a stiffness method, okay? Matrix analysis is a matrix stiffness analysis approach. Sometimes it's called direct stiffness analysis, but it's a stiffness approach. Does anybody remember the difference between a flexibility approach and a stiffness approach? I want to ask the chat that. I want to make sure everybody was paying attention during that last lecture. When we have flexibility methods versus stiffness methods, what's our unknown? I promise I would never ask a question like that on the exam. I don't know what you're talking about. I'd never do that. Stiffness methods, you're solving for the displacement. So exactly right. So the first thing that we need to do, is we need to solve for these. Those are our first primary unknowns. So how are we going to do that? Okay. Well, let's look at this. Okay. Now, first thing I want to do is I want to see if you all remember how to do matrix multiplication in general. Like, do you all remember the pattern? Like, if you have, 1, 2, 3, 4, 0, 8, and you're multiplying it by, 0, 9, 3, 6, 1, 2. Do y'all remember how to do matrix multiplication? So, you're going to have an answer here. And so the first thing that you do is you take that times that plus that times that plus that times that, and then that gives you 9, right? And then you do this times this plus this times this plus this times this, and that gives you that value. Do you, whatever that value is, and so on and so forth. Y'all remember how to do that? I know it's probably been a while, but this is like the pattern for doing matrix multiplication. Well, what I want to do is I want to take that process and I want to sort of apply it to what's going on in this system, okay? And I want to see if you all see something here, okay? So let me show you a different way of thinking about matrix multiplication using the system, okay? So again, it's probably been a while. I've probably done this maybe since high school or something, or maybe in some of your freshman level classes here at Marshall. But if you have a matrix multiplied by a vector, okay, so how do you get this term right here? You take this times this plus this times this plus this times this plus this times this, and that's how you perform matrix multiplication, and then you keep doing that. So if you wanted the 300, you do that times that plus that times that plus that times that plus that times that, okay, and so on and so forth. Well, what I want you to do is I kind of want you to keep your eye focused on this term, the 0 up top. And so watch what I'm doing. To get this first term, I'm doing that, 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 that. And then the second one, that, 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 and so on and so forth. So another way you could think about it is really what you're doing is every time you perform the matrix multiplication, this first term is being multiplied by all of these. And then this second term is being multiplied by all of these. This third term is being multiplied by all of these. This fourth term being multiplied by all of these. So if you wanted another way of thinking about matrix multiplication, you could look at it like this. Really, what we're doing, like all of this, is really 0 times this first column plus delta 2 times this second column plus delta 3 times this third column plus 0 times this fourth column. And then that has to equal everything over here. R1, 300, minus 125, or R4.
And this is going to fan out into a system of equations, right?
Exactly. You're exactly right. That's all a matrix, a set of matrix multiplication is. It's just a system of equations. But here's the ultimate point I want to make. Okay, we have this full-blown 4x4 system. Okay, now I'm gonna tell you right now, if you take this system and you say, okay, I want to just plug it into Microsoft Excel right now, so I'll invert this matrix, multiply it by that. Go ahead and try it, and it's not going to work. Okay, you're going to get Microsoft or Excel is going to give you an error, and it's going to say unknown, error doesn't work. Okay, if you go back to some of the matrix terminology we mentioned earlier, we have a term that we brought up in matrix algebra, the idea about whether or not a matrix is singular or whether or not it's invertible. Okay, I propose to you this matrix right here is singular right now. It doesn't have an inverse. The reason it doesn't have an inverse is because it represents a system that's unstable. The reason it represents a system that's unstable is because we have not imposed any boundary conditions on this system at all. Excel or RISA or any program looks at this matrix and it thinks, I just have 4 bars floating freely in space. But that's not what's really going on. In this problem, what's going on is joint number 1 and joint number 4 are fixed. They can't move. So what I've got to do is take this system and reduce it in a way that maintains stability of the system and represents the stability in real life. So let me show you how I'm going to do that. Okay. The first thing I'm going to do is I'm going to eliminate columns 1 and 4. So this is 1, 2, 3, 4, 1, 2, 3, 4. The first thing I'm going to do is I'm going to eliminate columns 1 and 4. So I'm going to eliminate that column, and I'm going to eliminate this column. And you're like, well, how are you able to do that? Well, I'm able to do that because look what happens here. What happens to this first column? Like what numerically happens? I multiply it by 0. Same thing over here. I multiply it by 0. So those terms don't influence the system at all. So I'm eliminating the terms that are multiplied by 0. They have no influence. Okay, so that's my first way of imposing boundary conditions. Okay, so what I'm ultimately going to be doing is I'm going to be striking out columns and rows. And so I want you to understand why we're able to do that. The way that we're able to strike out the columns is because when you expand it out, all these columnar terms are being multiplied by 0, so they don't contribute anything anyways. All right, now what about the rows? Which rows am I going to eliminate? Well, as Mr. Blizzard said, what we're doing here is, this is just a system of equations, okay? And so, if you follow this out, I'm going to have 4 equations. Why am I going to have 4 equations? Because there's 1 equation for each row, okay? So let's look at each of these equations. 2 of these equations, the ones in the middle, are going to be the ones that we use to solve the displacements, right? 2 equations, 2 unknowns. I've got 2 unknowns, delta 2 and delta 3. I've got 2 equations, 2 unknowns. I can solve those equations right now. The remaining 2 equations I'm going to use later to solve for the reactions. So what I'm now going to do is if I eliminated columns 1 and 4, I'm going to eliminate rows 1 and 4. And what I'm going to be left with is this, and this. I'm going to be left with a reduced system, okay? So if we go back to the notebook here, so here's the notebook. I am going to cross out, and the reason I'm crossing out 1 and 4 is because 1 and 4 are associated with the support conditions. All right, so cross out 1, 4, 1, 4. And so what am I left with when it's all said and done? I'm left with a KR of 300 minus 200 minus 200, 300. I'm left with a delta R of delta 2, delta 3. And I'm left with an FR of 300 minus 125. And so we call that R because it's reduced based on the boundary conditions. And it's a really easy process. So and all you do, this is all you do. You take the rows and columns that are associated with your boundary conditions, strike them out, and collect everything else into columns and vectors. So if you had a matrix that was 12 by 12, and you looked at them and you had degrees of freedom 1, 7, and 11 that were fixed, then cross out rows and columns 1, 7, and 11, and just collect everything into one big system. There's your system of simultaneous equations. And unlike before, this system is invertible. Okay, so what you can do is you can say, therefore, my displacements are taking my inverse of this times my forces, right? Because basically what I'm doing here is I'm saying, okay, F is K delta, right? And so if I want to solve for delta, multiply both sides by K inverse, right? Over here on the right, that cancels, K inverse times K cancels, and I'm left with delta equals K inverse times F. I'm just expressing it in terms of those reduced matrices based on the boundary conditions. So what do? I go into Excel, I invert this matrix, so M inverse of this times that. I'm curious if anybody has an Excel spreadsheet open if they want to do this. If you don't, you can. This system is small enough that you could break it out and do it in the Casio. You could just do your 2x2 equation solver and solve this out in the Casio. But I'm curious. I want to see if anybody can knock this one out for me real quick. This one isn't that bad. When it's all said and done, you should get delta R equals 2 values, and I want to see what those values are. And keep in mind the codes are 2 and 3. But I want to see if anybody has a value on that. Anybody got an answer for me? Not yet. All right, I'll give it a minute, and then I'll go ahead and just give you the answer. Don't worry, we're going to do this problem in Excel together here in a little bit. Okay, I'm going to go. All right, that looks a little tiny. You might need to make sure that you're inverting your matrix because you got to do M inverse on this one. Right, so you're doing M multiplication, but yeah, that's a bit big. The answer should be you should get 1.30 and 0.45. Okay, there you go. Yeah. All right, now I'll tell you what I'm going to do just to sort of round out what we're doing here is I do want to show you a couple things in Excel. So give me 1 second. All right, so I have here an empty spreadsheet. And so I just want to show you something real quick. There's nothing special about this. I just threw some colors on it and made it empty so that you could kind of see what we're doing here. So just so you're aware of what I'm doing, right? So let's take this first matrix. This is 100, that, and that. So what I did is I set up some formulas here so that, for instance, if I change this to 64, it automatically changes all the other stiffness terms because I'm lazy. So I can go ahead and, put that there and there and, fill out my terms. What I want to do is just show you a real quick shortcut on how to do the assembly and how to do these multiplications. So this is quick and dirty. I'm not, too worried on format. So if you remember, stiffness matrix number 1 goes from 1 to 2, and this goes 1 to 2 right there. If you're lazy, you can say equals transpose of those so that your member codes show up. Same thing with the other two. This one goes from 2 to 3. This one goes from 3 to 4. All right. Now, what I want you to pay attention to is this part right here. Let me move the formula bar. I want there to be some visible screen here. Okay. So if you recall, the way the assembly process works is I place the terms where they go inside the global stiffness matrix. So what I can do is I can set, I can say, okay, element number 1 goes here. That's where it goes inside the full-blown stiffness matrix. Element 2 goes here. Element 3 goes here. And then what I'll do is I'll say, in order to assemble them, because I've placed them where they go, I'll just one for one, cell by cell, sum up all the associated cells, even if they're empty, because I'll copy and paste this formula across the board. And bam, there's your assembled stiffness matrix. Because I placed them where they go inside the full-blown matrix, there you go. And then in order to apply the boundary conditions, what I'll do is I'll use some creative formatting, and I'll say, let's just do this, and hold on, this, and this, and let's cancel those out. This and this, cancel those out. And so this is one of the reasons why I really like Excel, is because you can visually assemble it and then just use cell formatting to say those are the ones I'm knocking out. And so this is my stiffness matrix. And then in order to determine the displacements, we had a load vector of 300 and minus 125. Now watch what I'm going to do here. Okay, and this is what I'll leave up here for a bit. So we're going to do equals. We've got to do matrix multiplication of the inverse of this. So the inverse of that times that. Right? That's ultimately what we've got to do. And so when we press enter, that's what we get, as Mr. Enoch said, the 1.3 and the 0.45. I know I went through that Excel stuff kind of quick, but that was sort of the reason that we did that one practice assignment, so that you get up to speed on a lot of the matrix multiplication. Does anybody have any questions about this? I want to take a second, see if everybody's clear on this. I can go here and see if you need to type that formula out or you want to write that down. All right. Any questions? Don't hesitate if there's something that's a little fuzzy. Okay. All right, so let me stop this share. Let me go back to the notebook. Okay, so these are the displacements, okay? And I want to be clear, we now have the displacements for every joint in the structure. We're already done with that. We know that joint 1 has a displacement of 0. We know that joint 2 has a displacement of 1.3. Which direction is that 1.3? Is it to the left or to the right?
That would be to the right.
Exactly right. It's to the right because it's positive. Joint 3 has a displacement of 0.45 inches. Remember, kips in inches. Everything's consistent units. 0.45 inches to the right. And joint 4 has a displacement of 0. So right off the bat, we have the deflections of every joint everywhere. No, method of virtual work to determine the deflections. We have them all of them everywhere in one fell swoop. Now, here's where things get pretty slick. Okay, so watch this. We have 2 remaining things to do. Okay, the first thing to do is let's determine internal member forces. Okay, now we know that delta R is 1.3 and 0.45, right? And that's based on, joint 2 and joint 3. So what I'm going to do is I'm going to form a big old displacement vector for the whole system, right? And that big old displacement vector is basically going to be the same thing, just putting zeros on all my joints that have support conditions, right? So delta, the big delta, remember, if you scroll back up here, I had already written that like up here. I'm just rewriting it, with the whole system. Now what I'm going to do is I'm going to take this and I'm going to break it up as follows. Would you agree that if I have a displacement vector for the entire system, that I could write a displacement vector for each of the 3 elements? Right? Element number 1 goes from 1 to 2. Element number 2 goes from 2 to 3. Element number 3 goes from 3 to 4. I'm just using those member codes. Everybody see what I did there? That little 1 there on that one subscript was kind of difficult to see. So that's a displacement vector for each of the elements in the system. Here's where I'm getting at. Watch this. Okay, let's take element 1. All right, remember there's 3 elements in the system. Okay, element number 1, if you remember, had a K matrix that was like this. Right, and this was 1, 2, 1, 2. And now we have a displacement vector that's like this. So if F equals K delta, maybe what we ought to do is multiply these, right? Now, no inverses. We don't need to solve anything. We're not solving a system. We're just back. This is back substitution. This is just plugging and chugging. So I'm curious. I want chat to help me. What do you get when you do this? And you could do it visually if you wanted. But I want to see what you get. Negative 130, 130. That's right. But what does that mean? Let's see what that means. Here's element 1. I got a force here that's negative 130 and a force here that's positive 130. That negative 130, which way does that negative 130 point? To the left. What about that positive 130? Which way is that point? That's right. That's going to point to the right. So what does that vector mean? One value for each degree of freedom. That's true. But what does this vector mean? If I have this, what does that mean? 130 kips. What does that mean? In tension. That's exactly right. You are exactly right. 130 kips in tension. Okay. Watch this. Let's do the next one. Let's do element 2. Right? So K2 was 200, negative 200. And this was 2 and 3. And then delta 2 was, now this one was 1.3, 0.45. And this was 2 and 3. So somebody help me out. You've got Excel there with you. What does F2 equal? -170, negative 170. So I'm seeing a pattern here, okay? Whenever we solve for our force vectors, we get two numbers. We get equal numbers, but they're opposite signs, right? So like a 130 and a negative 130, or a 170 and a negative 170. But now let's see what this means, okay? So here's element 2. So we have the first one is 170 going to the right, and this over here, 170 going to the left. Well, what does that mean? Compression, there you go. So this one, 170 kips in compression. Boom. And so you could imagine how a computer does this. A computer is just going to loop through this, and it's going to form a vector and multiply, form a vector and multiply. It's just going to do this automatically. It gets kind of almost boring and rote at this point. So let's do element 3. So, and I'm going to show you something that's really cool here in a bit. So, anybody just know what this is going to be? Has somebody already done this math? I'm going to show you something that's really slick here in a bit. $45 and $45. Yeah, $45 and negative $45. That's exactly right. Now, can somebody just look at that vector and tell me whether or not that's going to be compression or tension? It's compression. That's exactly right. And you want to know a really easy way of doing this? Whenever you do these problems, if you just look at the second number, if it's positive, it's in tension, and if it's negative, it's in compression. So it's just a little shortcut, right? Because we consider tension to be positive, compression to be negative. You could just look at the second number and see whether or not what it's going to be. So this is 45 kips. In compression. All right. This is good stuff. Hey, you want to see something really slick? Watch this. So, watch this. Watch what happens when you assemble the results. So 1, 2, 2, 3, 3, 4. Now I'm curious if the chat can help me. What do you get when you assemble these results, right? And what do I mean by assemble? There's going to be a 1, a 2, a 3, a 4. I could do a little better on that little squiggly bracket. So, like, we're going to have, F1, F2, F3. So somebody help me out with the 1. What's the 1 going to be? The F1. Like, what is that term going to be? Negative 130. All right. All right. All right. What about 2? 300. What about 3? negative 125, negative. What about 4? Negative 45. That's exactly right. Huh. Well, think about this. I want you to look at this, and then let's look at that. Huh. It's almost like we've already got the reactions. R1 and R4. R1 is negative 130. R2 is negative 45. And if you want something really crazy, add up those 4 numbers. Tell me what you get. You get 0 because the sum of the forces in the x direction is 0. So watch this. Summary. We have every reaction. We have every internal force. We have every displacement. The entire structure is solved. There's nothing left. That's everything. You want to know what RISA does? That's what it does. We have every reaction, every internal force in every member, every deflection, all of it. It's all solved all at once. When you click the equals button, this is what RISA does. I want to see if there's any questions on this. Maybe I'll put this, maybe I'll add something up here. Just to relate it to what we had before. I want to take a second and see if there's any questions. I didn't get a chance to talk about trusses and local versus global. That's fine. We'll do that on Wednesday. We got plenty of time on that. I do want to bring up the homework, though, so if there's any questions, let me know, because I want to show you something on the homework. Fix that. Well, I'm going to bring that up. Okay, so is everybody good on this? Will we go about the same method for the homework? Yes, you will. Let me bring up the homework real quick. Okay, so all right, so here's the homework assignment. And if you notice, so the one thing that I did with the homework assignment to make it maybe a little complicated is I just made the connectivity a bit different. Okay, so there are 6 elements and there are 5 nodes. So first off, the full-blown K matrix is going to be 5 by 5. Now, let me show you, and I'll show you for the sake of discussion with element number 3 so that you all kind of have an idea. And I think if you see this, you'll see it's not that bad. So let me stop this share. Let me share like just a whiteboard. So if you look at, let's say, homework. So element 3, I think it was that I gave you, was, oh God, I'm going to get the numbers right or wrong. Hold on. I know we're running out of time. I'm hurrying. Okay, so element number 3, I gave you the stiffness matrix. It was 5, minus 5, minus 5, and 5. And then the member codes that I gave you were 2, 4, 2, 4. Okay, so when you assemble the full-blown stiffness matrix, the full-blown stiffness matrix is going to have 1, 2, 3, 4. 1, 2, 3. So this is going to be your full-blown stiffness matrix. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Those terms are just going to go here because that's where they are in the assembly. Okay. If, so for instance, element number 2 goes from 3 to 4, right? So element number 2, K2, goes from 3 to 4, and it's going to be 1. So 3 to 4. So that one's going to go 1, minus 1, minus 1, and then plus 1 because you add it there. And so that's where that term goes. Okay. And so you just keep assembling. Now, as for the boundary conditions, for this problem, you eliminate rows and columns 1 and 4, right? So you're doing 1 and 4, 1 and 4. And so all you do is you take that cell, those cells that are left over, and collect them into a KR. So it'll be 1, 2, 3, 4 over there, 1, 2, 1, 2, and then 1. So it ends up being 3 by 3. But it's the same process. It's just the assembly is a little weird. The idea is that if you understand how to do this, you certainly understand how to assemble really anything. It's just pattern matching at that point. Did that clarify a little bit? I know we're really running out of time, so I'm going to have to stop it here in a bit, but are you good on that? Okay. All right, I'm going to stop the recording. If you all need anything, you let me know. I'm available through Teams and whatnot. But that's all I've got, everybody. I will see you all. On Wednesday, and we'll talk about trusses on Wednesday. All right, we'll see you then.